Okay, so we continue with our WiMAX activities and looking back at this WiMAX model. There are so many states in this system. You have W0 states in the back-off stage here on stage 0. You have M plus 1 plus M plus 1 states in the weight plane in stage 0. And there are multiple stages. There's a second stage as well. So there's a large number of states. Furthermore, if you change the parameters, if I change M and I change W, then I'm changed the number of states. So you can imagine this would be very difficult to model in Excel. So we want another strategy. And the strategy is I'm actually going to replace this whole block with a single state. And I'm going to replace all of these x's with a single state, and all of these y's with a single state. Okay, so let's see how that works in the following. All right, first we want to look at the back-off stage. Now, if you remember, the back-off stage had W states. In the system model, they're labeled from 0 to W0 minus 1. And in this representation, I've labeled them from 1 to W. The labeling is not important as long as I consider W states altogether. But you can see that this model is the same thing. When you enter the back-off stage, you enter any one of these W states with equal probability. And then once you've entered, you move to the left with probability 1 at each clock tick. Okay, so I'm asking several questions about this system. One thing I'm asking about is the transition matrix when W equals 2. Okay, so let's take a look at that. So you can see how that's done. So here's my system, and I want the transition matrix for the case where W equals 2. Okay. Now I think I specified what the ordering of the states should be. Yeah, so I'm going to order them this way: B1, B2, and A. All right, so the transition matrix. So let me just do the diagram. If there are two states, then it's just going to be A. And then I'm going to go here with probability 1/2 and here with probability 1/2. And here's B1. And here's B2. And then this is probability 1 going here. And then this is probability 1 going here. All right, now, since I'm going from state to state, I'm going to have a 3×3 transition matrix. Sorry about the sloppy writing here. This is 1/2. This is 1/2. This is B2 here. It's 1/2, 1, and there's 1 here too. Okay. Now I have a 3×3 transition matrix. Why is that? Because I'm going between states, and the states are related. So I'm going to label my columns B1, B2, and A, and I'll label my rows B1, B2, and A. Now, the columns you should think about as saying from which state you're coming. And the rows you should think about to which state you're going. All right? And then you'll put the numbers in corresponding to the from and the to. Okay? And you just have to make sure that you cover all the arrows. For instance, this one here. This arrow here is going from B1 to A. From B1 to A. What does that mean? B1 from A to. Put a 1 here. Okay. Here we have two arrows from A, from A to B1, from A to B2, what does that tell me? From A to B1, there's going to be an entry here. From A to B2, there's going to be an entry here. Okay. So you should be able to complete the entire transition matrix in this way. Make sure you have 1, 2, 3, 4 non-zero entries. Okay, so that's how you get the transition matrix from the diagram. Okay. All right, now once you have the matrix, you should be able to find the eigenvector. Okay, I'm telling you that there is an eigenvalue 1. You should, and that's related to the fact that for every one of these states, the sum of all arrows going out of that state is 1. Like for instance, A here. Here we have 1 over W, 1 over W, all the way up to 1 over W. The sum of all of these exit arrows is 1. So I'm asking you to find the eigenvector with eigenvalue 1 such that the sum of the eigenvector's entries is 1. Remember that any multiple of an eigenvector is an eigenvector. So you're going to have to find the multiple that satisfies the condition that the sum of the entries is 1. Now this eigenvector is called the equilibrium vector, and it's interpreted as the probability of being in each state after a very long time. So for instance, if I had an equilibrium vector that's 1/3, 1/3, 1/3, I'm not saying that's what it is, but suppose it was 1/3, 1/3, 1/3. That would mean that there's a probability of 1/3 of being in any one of the 3 states in the long run. You're equally likely to be in any one of the 3 states. Okay, so you do that for the case where you have W equals 2, which has 3 states total. And I want you to repeat these 2 parts for W equals 4. So that will be 5 states total. Now you're going to get a formula for the eigenvector here and the eigenvector here. I want you to infer what will the eigenvector be for arbitrary W. All right, look at the formula for 2, look at the formula for 4, and see if you can generalize that. Okay, if you can't, then you can do a couple more W's. But I'm not asking you to prove this. I'll just ask you to infer. Okay, so make a guess based on the pattern. Now, for the equilibrium vector you found in B, that's 4, W equals 4. What is the long-term probability of being in state A? Now remember, long-term probability has an interpretation in terms of the equilibrium vector. So you should be able to get this long-term probability from the equilibrium vector. Okay, so we've characterized in some sense the back-off stage. We've characterized the expected time. And we've also characterized, if you hook this back-off stage up to a single state, we've characterized the fraction of time that the system will remain in this other state. I want you to do the same 2 calculations for this simplified 2-state model. Okay, so what's the difference between this model? Note that this model has a state with an arrow going back to itself. Right, from B1, the part of it goes back to itself and part of it goes to A. And the point is, eventually, is that I want this single state B1 to represent all of the states in the back-off stage. Notice that if I'm in the back-off stage, there are 2 possibilities. Either I'm going to go out to A, or I'm going to stay in the back-off stage. And those 2 possibilities are reflected here in this single state. I have a probability A of going out, and a probability of staying in. Okay, so here you're supposed to do the same sort of computations for this simple two-state model. And then what I want you to do is figure out how to make this two-state model mimic most closely the behavior of this more complicated model. And eventually we're going to replace this more complicated back-off stage with this simple model. Okay. Right. I'm going to do the same thing with the weight plane. Okay. So here we have a system model for the weight plane. Actually, it's just the upper part of the weight plane, the states with x's in it. And if you notice, these probabilities are the same probabilities that we found in this line of states here on the weight plane. Right? You have 1 minus q going to the left and q going out. Same thing here. 1 minus q going to the left and q going out. The last one, it goes out with probability 1. Okay. So notice there's actually going to be m plus 1 states in the weight plane here, depending on m. Okay. And here I'm asking for some similar facts about this system. I want you to find the matrix and the equilibrium vector for 3 different cases, m equals 1, m equals 3, and m equals 5. I want you to infer the equilibrium vector and then do similar questions for this system. And I want the upshot of this is going to be to find a version of this two-state model that can replace this more complicated weight plane. Okay, so now we're going to implement these simplifications. Here's my original system diagram, and I'm dividing it up into 1, 2, 3, 4, 5, 6 states. And as I just said, we're going to replace these bubbles with single states. And that's what's done down here. This x0 up here that has m plus 1 states, I'm going to replace with this single state x0 here. This x0 has one arrow going out. That means access is granted. It has another arrow going down, which means it's passed on to the next weight plane. And then it has one arrow going to itself. Okay, that corresponds to the two-state system here. So this B1 is like my x0. The only difference is that here I have one arrow going out, and here I have here I have one, let me go to the simplified system, sorry. Here I have two arrows going out. But you can think of these two arrows as simply the single arrow split up into two parts. Essentially, you have arrow going out, which is actually two arrows, but you can think of their sum. And you have arrow returning back to itself. Okay. All right, so I've simplified this really complicated system into a system with actually 7 states. This you could call this 7-state limbo. This is where people didn't get their request acknowledged and they're kicked out of the system. They'll have to go back in again. Okay. What I want you to do for this table is to put values of these parameters in terms of the parameters that are given in the original system. Okay, let me see if I can do an example here. Well, this AB0, for instance, what does AB0 correspond to? AB0 is the probability of going out here. Now, what you have to do is you need to figure out what single state, what value of A here, what value of A here is a good replacement for this system here. Okay? And that value of A here gives the sorting, the exit probability from this state B here. Okay? This exit probability corresponds to the exit probability here. You should be thinking about this single state. This single state represents the weight plane. This is coming from outside the weight plane. This is what cycles back to the weight plane, and this is what leaves the weight plane. So the value of A that you found in the previous exercise, the value of A that most closely mimics the behavior of this back-off stage, is what you want to put in for AB0. I might have called this the weight plane. This is the back-off stage, of course. So if I said weight plane, then please replace that with back-off stage. Okay, and I want you to do that for the same thing for all of these. Right? This x0 is a single state that replaces all of the states here. This y0 replaces all the states here. You should be able to find these parameters, ax0, ay0, and etc., based on the best replacement for these multiple states with a single state. Okay, and your answers here in this table are not going to be numerical values. They'll depend on these parameters, Q, M, W0, W1, and so on. You should notice here that I have done a different M for stage 0 and stage 1. So you should consider the possibility that this M is different from this M. So let's call this M0, and we'll call this one M1. Okay. All right. Now you have all of the information that you need so that you should be able to implement this system. I'm not going to show you any sample. I want you to take all this information and use all this information to construct your own spreadsheet model for the system. Here I've given you the initial values. Remember, I said there are 7 states here. 1, 2, 3, 4, 5, 6, 7. And I want you to start with 100 users in this state. And these are the parameters I want you to use. You should be able to find all the system parameters in terms of these parameters. Now, once you've constructed your model, you should be able to work with it. Use your model to show that the total number of users remains constant throughout the process. Okay. I want you to use your spreadsheet to find the largest eigenvalue and the corresponding eigenvector. Okay. Remember, we've done similar things in the spotted owl model. I want you to use your spreadsheet to give evidence for the presence of complex eigenvalues. This is actually I want you to compare this, what you see, with what we saw in the spotted owl model. All I can say is that when you had complex eigenvalues, you saw some wiggles. So I want you to see if you can relate that concept to this model as well. Okay. So you need to explain how you can show their complex eigenvalues from what you see in the spreadsheet. Okay, now here's the hard problem. I want you to actually use the spreadsheet to estimate the magnitude and phase of a pair of complex eigenvalues in the system. Okay, I really expect that most people will not be able to do this problem. But I include this because in practice, you do encounter difficult problems. And it's a very interesting problem, and if you think about it, I think you can do it. Okay. Then here I want you to construct the transition matrix for this system. You can see we have 7 states, so that tells you something about the size of the matrix. That seems to be a very big matrix, but remember, most of the entries are going to be 0. Then I want you to use Wolfram Alpha to find the eigenvalues and eigenvectors for the matrix. As I said in my email, this activity will take 3 weeks. I'm sorry. This model will take 3 weeks. All of these activities together, and I will have one more activity that asks you to work more with the spreadsheet itself, and that will be due in 3 weeks. All right. So that's it.